Amperage is the flow or volume of free electrons moving through a conductor. All right? In the water side of the deal, the analogy, it's gallons per minute or gallons per hour. You have a physical material or substance that is moving. It has weight, takes up space, volume, whatever you want to call it. All right? With electricity, it's electrons, free electrons, moving through a conductor. So the analogy, once again, holds up just really well, really well. So flow of water and flow of electricity. Flow of water is measured in gallons per minute or gallons per hour. Electricity is measured in amps or amperes. Okay, that's amperage, and that's something that we as a technician are going to measure every day. It's one of our really big indicators of what's going on in the electrical side of a system. Voltage is the pressure that causes the flow, just like pump pressure or hydraulic head or whatever you have forcing pressure on this hose. That's one thing measured in PSI usually. For electrons, it's voltage. All right, remember, you've seen this before if you've seen the earlier parts. An electron is a real piece of something, and it is. It's part of an atom structure. It has weight, takes up space. And back to this part of an atom structure, electrons are a part of every atomic structure. Every one of them has electrons in the outer orbit. Otherwise, it wouldn't be an atom. All right? It just happens that copper and other good conductor materials have that free electron. Okay? That's the big deal there. Electron has weight and takes up space. 1 ampere of electrical measurement is 6.24 times 10 to the 18th power, flowing past a point in a conductor in 1 second. Approximately amount it would take to fill a small thimble, and approximately the same size as a .45 caliber bullet. Electron flow in conductors. An electrical conductor allows electrons to flow freely across its surface. Once again, we're back to copper, or we're back to maybe aluminum. But you're not going to see aluminum in much wiring other than the utility side. They use aluminum. The larger the cross-section of the conductor, the more amperage electron flow can be moved safely along the conductor. And the big word there, as it's sort of highlighted, safely. You can move lots of electrons along just about anything if you have enough potential difference. Remember, the pressure is potential difference. All right. But the other side of that factor is safely moving along the conductor. And there's a lot of issues there that we'll continue to talk about. NEC stands for the National Electrical Code. It has many tables that specify how many amperes or amps can be safely moved through the conductors of different sizes and materials. Here's an AWG, American Wire Gauge. Here's an actual gauge, and actually I still have it. I got it right here. Note that the smaller the gauge number, the bigger the wire diameter. And that's, you know, sort of backwards in the big scheme of things, but that's the way they did it. Smaller numbers indicate larger wire diameters. Here we've got a 10, and then as you go down in number, the size of the wire gets larger and larger until you get up to the 0, which is an aught. They call that an aught in wire gauge size. Resistance. The difficulty electrons encounter in moving through a conductor or substance. The opposition to current flow, measured in ohms, its symbol is R, or the little omega sign. And more than likely you'll see the little omega sign for ohms resistance. All right? Once again, we're back to the water analogy, electric system versus water system. And the analogy of resistance to flow in the water system, of course, is the nozzle right here, or restriction in the pipe. All right? The nozzle restricts the amount of water that flows, restricts it based on whatever pressures in the water system. That nozzle is going to restrict the flow. If you took the nozzle off, the flow would be free and easy, but we've got the nozzle there. All right? Same thing with electricity. All right? Here's the restriction in the conductor or the circuit, and it's going to restrict how many electrons flow through that circuit. The little images, of course, here's a light bulb. The light bulb, in this case, it's a very simple illustration, but that is a load. You put a light bulb in a potential different situation and it's going to light up, okay? This symbol right here, the zigzaggy thing, that's an electrical symbol for resistive load, okay? Here you go. Loads equal resistance to electron flow. Electron flow that is pushed by voltage is the work or the purpose of the use of electricity. If we don't have a load to do something with the electrical energy, then why do we use electrical energy? Every circuit that you ever work on will have a load in it, okay? And I've got some examples. The light bulb, motor, and heating elements shown in the schematic symbols are all considered loads that do work by converting the electron flow to another form of energy. The resistance to electron flow is what keeps the electrons in control. Without resistance, without a load in the circuit, in other words, the flow of electrons would be, as it says, massive and destructive. If you don't have a load, something that checks, something that controls that electron flow in a circuit, the circuit is going to poof. It's going to get very hot very quick, and there's going to be a lot of sparks involved. Okay.